here's the second part of the energy, quantitation of energy exchange, otherwise known as a million ways to calculate enthalpy. So here's another way, and this is called Hess's Law. And it's a series of elementary reactions that you use to get your target reaction. So if we would like to know the enthalpy for this reaction, and we are given these baby reactions, also otherwise called elementary reactions, we can manipulate these reactions until they add up to this one. And likewise, whatever we do to these reactions, we will do to the delta H that's associated with it. So this is how we do this. These are puzzles for smart kids. So the first thing that we want to do is we want to look at the elementary equation and see if we want it to run this way or if we want it to flip. So if these are the reactants and this is the product, to flip it, this would be the reactant and that would be the product. So when I look at it compared to my target reaction, I see that it has, on the reactant side, two things that I want it to have. So I'm going to leave it as it's written. So just quickly rewriting it, I have this, and since I did nothing to this reaction, I will do nothing to the value of delta H for this elementary reaction. When I look here, I see that I want to have carbon monoxide as a product, not as a reactant. So I'm going to go ahead and flip this equation and rewriting it this way. It always makes a little more sense to me if I keep the arrows aligned. It's easier to see what I'm doing. So I reverse this reaction, so I will reverse the sign of delta H. Now I'm going to look at these two reactions and add them together. I'm going to recall that anything that appears exactly the same on both sides of the arrow are called spectator ions and may cross out. CO2 is a spectator ion. It is gaseous on both sides of the arrow. I have 1 mole of O2 here and half a mole of O2 here. This 1/2 a mole will cancel out half a mole on the product side. And when I look at this, I see that when this adds up, I have my target reaction. So I have been successful in manipulating them. And now I will add up these two values to get my delta H. And my delta H value will be 110.5 kilojoules per 1 mole. Let's take a look at this one. It looks a little more challenging. So here I have 3 elementary reactions, and I need to manipulate them until they add up to my target reaction, and this is my target reaction. So starting off, I have C2H2 as a reactant, and I want it to be a product. So I'm going to go ahead and flip that right now. So 2CO2 plus some H2O will yield C2H2 plus 5 second O2s, otherwise known as 2.5 O2s. So I will now reverse the sign of delta H since I reversed the direction of this reaction. Now when I look at the second target reaction, we definitely want to keep it as it is because both of these reactions have carbon as a reactant, and that's what I'm looking for. I have done nothing to this reaction, so I leave delta H alone. Now, I don't see water anywhere in this reaction at all. I know it needs to cancel out. I have water up here, so I bet you I'm going to need water over here. I see in this elementary reaction I have hydrogen as a reactant, and I have hydrogen in my target, so I'm going to leave this as it runs as well. Okay, I'm going to leave this alone too. So now I have determined the direction of flow of all three of my reactants, my elementary steps. Now I need to look about coefficients. I'm going to hop down to this one because I see my target reaction has 2 carbons and I only have 1. So I do know that I need to multiply all of these by 2 in order to get 2 carbons. And that means I will also multiply my delta H value by 2 as well. And that one step produced success. When I look at this 2 cross out spectators, 2 CO2 crosses out 2 CO2, 1 mole of water here crosses out 1 mole of water here. Together on the reactant side I have 2.5 oxygens, which will cross out these 2.5 oxygens, and what I should have left are the sum of these elementary reactions that should add up to my target reaction. And it does. So the only thing I need to do now is to add these up. And when I do, I find the delta H of this reaction gives 226.8 kilojoules per mole. This is an endothermic reaction. And I think we're ready to move on to one of the most confusing parts of chemistry.
Teachers, please.
The last time.
No problem, I'm going to do it anyway. Okay, the following teachers need to load all senior grades. Please come to the registrar's office to see what sections you're missing. Miss Baumgart, Miss Harding, Mr. Key, Mr. Nelson, Mr. Griffin, Mr. Ray, Mr. Okay, and will you please go to the registrar's office and Miss Walker, Riddell Walker. Thank you. Sorry, Aaron Walker. Thank you.
All right, so bond energies to find enthalpy are a little bit different. In this case, it's the reactants minus the products. Bond energies are the energy that you need to break a bond. So all of them are endothermic. What you must do is take your target reaction and actually sketch out the bonds between them. H2 is another way of saying you have 2 hydrogens that are connected by a covalent bond. Reacts with diatomic fluorine, 2 fluorines connected by a covalent bond, and it will produce 2 molecules of hydrogen bonded to fluorine. So all we do then is tally. We have 232 kilojoules per mole needed to break this bond, 154 kilojoules needed to break this bond, and then when these bonds are formed, we have 2 times 565 kilojoules of energy. All right, when we tally this up, we have a negative 544 kilojoules per mole associated with this reaction.